Right, so Justin, let me begin. Um, the first question, the battery in an electric car can be charged by passing a current of 11 amps through it. Calculate the charge stored in the battery after 8 hours. What is the formula for charge?
Well, for charge is Q equals to IT.
Right, Q is charge, and what do we measure charge in?
Coulombs.
Coulomb, right? So you have to put those units and you get your final answer. So what is my current?
The current is 11 amps.
What is the time?
Time is 8 hours.
Right, 8, and we convert that to seconds. We multiply 8 by, tell me, we multiply 8 by,
8600.
right. The reason we say into the 600 is because it have 60 minutes in an hour and 60 seconds in 1 minute. 60 by 60. So what is your final answer?
28,800 seconds.
Nah, we doing everything one time. So tell me your final answer.
Oh, 2,800 coulombs.
Come on again.
316,800.
316,800. And
800
where's the units?
coulombs. Well,
Coulombs,
C.
nice. Right, calculate the resistance of the battery given that the voltage used is 220 volts. So, anytime you see voltage and resistance, V is equal to IR, right? So, I want to make R the subject of the formula. So what I would do is, I would divide both sides by I. Now, if I divide both sides by the I would cancel off over there. So that would leave me with R is equal to V over I. Just to show you all I mean, watch. Oh, sorry. So R would be equal to V over I. So you can see it there for yourself. So do I know what the voltage is?
Yeah.
Well, what's the voltage?
220 volts.
All right, and what's the current?
Current is 11
What's the answer?
amps. 0.05.
Mm-mm. Your answer was wrong because you had 11 over
Oh, yeah.
220.
20.
Right, because 11 into 22 is 2, so 20. And what's the unit for resistance? Very important. You need to put the units.
Ohms.
Summer?
Ohms.
Swah. Right? Cool. Cool. Right, let's move on to our next year. Give my year.
2021 January.
Hmm. I think 2021 January, but I do have 2021 May, June.
Yeah.
Okay, this question here, I didn't teach you all everything to be able to do that one there. Um, yeah, you all don't know how to do that yet. You all should be able to work some questions though. Let me explain. You remember when we did waves?
Yeah.
Okay, nice. So let me do this question and I think we should be able to do it. So calculate the value of the frequency for the generator. So we have a wave, and you see any wave?
Yeah.
How much oscillations you see in here?
Three.
Three. That's perfect,
Wait. Oh,
right?
yeah.
Three. Yeah, we have one here, right? Then we have one here. Nice. We have one here as well. We have three. Cool. So when we talk about frequency, do you remember the formula for frequency? Frequency is actually equal to 1 over what?
1 over t.
Yeah, 1 over t. And t is the what time?
T is the period time.
Wait. Okay. All right. Flexing on them. All right. And what's the periodic time? That's the time it takes for.
One oscillation to be completed.
Way. Oh, right. Off topic. You see the fight between Mike Tyson and Jake Paul? You hear about that?
Yeah, I want to watch it. I want to watch it.
Mike Tyson got beat that boy so bad.
Yeah, yeah, no competition. Yeah, no competition there.
There's like a father and a son. It's like the son thing, he better than the father. But yeah, you say it.
He
I
can
feel
win
like
that.
one hard slap from Mike Tyson and he got knocked down.
Yeah, Tyson, he's a horse.
Yeah, yeah, yeah. Right. So what is the periodic time here? What is the time it takes for one oscillation?
Um,
Look at the graph.
0.1 second, 0.01 second.
That's one oscillation.
Oh, wait. Oh, no, 0.02.
Right. That is one oscillation. Remember, an oscillation is one crest, well, it is a crest followed by a trough, right? So, and 0.02 what? That time is measured in what?
Seconds.
Right. So to find my frequency, that'll be equal to 1 all over the
0.02.
0.02. So log that into your calculator and remember, what is the units for frequency? You should know this from music.
50 hertz.
50 hertz. That's a nice base frequency.
Yeah.
You know, it have this real nice bass song. I think it's 3 6 Mafia. Um, I don't know if you know about it, but if you want to test the lows in the car, that's the song you play.
I'll try.
I will send you.
Yeah.
Yeah, ready for the bass line in that song. It wouldn't sound good if your system not made for lows though.
Uh,
Oh, I don't know what was he tuning for your dad's box? That's physics as well. What's he tuning? You know?
nah, he gonna know. I wouldn't know.
Oh, all that is physics. Physics is the best. Right. The peak voltage is applied to the generator across a 100 ohm resistor. Calculate the peak value of the current in the resistor. Let me understand what's going on. So they're talking about voltage, they're talking about resistance. What formula you think you might have to use?
V equals to IR.
Yes. Okay. Do we know what your resistance is?
Yeah.
What's your resistance?
100.0.
So be it just 100 ohms, right? And they're talking
Yeah.
about what voltage? What voltage in particular?
Peak voltage.
Peak voltage. Look at the graph. What's the peak voltage?
200.
Yeah. 200 is in fact the peak voltage. So let's write that down. And where's the only thing we don't know?
Only thing we don't know is the current.
And what do they want us to find?
Calculate the peak value of the current of the resistor. So current.
Right. Current. How are we going to find for current? Let's see. So we want to make I the subject of the formula. How are we going to do that?
I could be um R over V or VR, VOR.
V over R, yes. Because if I want to find for I, what I have to do on both sides? What is blocking the I? What blocking the I?
The V.
The V. If
Oh
I
no,
want to
the
make
R.
I the subject, what prevents an I from being the subject? Look at
R, the
IR.
resistance.
Yeah, the resistance. So we have to divide both sides by R. And when you do that, where's I now?
I is V over R.
Yes. We know that the voltage is 200, and we know that the resistance is 100. So what's the formula for the peak current?
Two.
Right? You could write I and in like very small, you could write peak. So I peak is equal to 2 watt. 2 watts. Yeah, tell me. What do we measure current in?
Current is
Again, you should know it from
um,
power to your
no amps.
amps. Yes. Nice. All right. Read part C.
The generator is subsequently rotated at twice the frequency in B part one. State the effects this will have on the period of the output.
Okay, so let us look at the formula for the frequency. Frequency is equal to what over what?
Frequency is 1 over I, 1 over T.
Okay. So, and if I were to make a TD subject of the formula, T would be equal to what? Do you know? Some might be a little tricky, yeah? Or would if I make TD subject of the formula, what would that be?
F multiplied by 1.
No. If I want to make T the subject of the formula, I would have to get rid of it from the denominator. How am I going to get rid of T from the denominator?
So
Yeah, you could flip both sides. That's the easiest way. So if I flip F, it will be what now?
um, T over 1. Well,
Say that again?
T over 1.
Wait, if I flip F, I flip F, what will it become now?
1 over F.
Right. So 1 over F is equal to T over 1. Where's T over 1? T over 1 is just what? If I ask you, where's 5 over 1? What you gonna tell me?
5.
5, right? So where's T over 1?
T.
Right. So that's what T is. So let me ask you a question, right? If I rotate at twice the frequency, so if I increase my frequency by 2 times, watch again, I increase my frequency by 2 times. What I do into the periodic time? You see any fractions here?
Yeah.
It what we do to the periodic time. So before it was 1 over F, and now it's 1 over 2F. So what I do to the periodic time?
You have in the
I
frequency.
go half the periodic time. Watch again. 1 over F is equal to T. But if I increase my frequency by 2 times, my periodic time is now a half of what it once was. It's an inverse relationship. Let me explain that one more time. And let me try to understand it. Periodic time, right? And periodic time is the amount of time it takes for one oscillation.
Yeah.
And frequency is the number what?
Frequency is the amount of oscillations in 1 second.
Right. So if the periodic time is less, what I'm saying is if the periodic time is less, that means it have more oscillations. If you understand what I mean. If I say the periodic time is one minute. What I mean is, if, after 1 minute, it would have an oscillation. But if I say the periodic time was like 10 seconds, then how much oscillation they gonna have in 1 minute? Let me see if you can figure that out. If if in
Period
if
time
in
is 10 seconds.
yeah, the periodic time is 10 seconds, and you have
Six.
a minute. Six, right? Six. So if I if I decrease my periodic time, what's gonna happen to my frequency?
Decrease the periodic time.
So yeah, if I decrease my periodic time, what's I doing with my frequency?
Decrease any frequency too.
No. Listen to the example again. If my periodic time is 1 minute, then how much oscillations go happen in 1 minute? If my periodic time is 1 minute, how much oscillations you gonna have in 1 minute? It's not tricky question. If my periodic time is 1 minute, how much oscillations you gonna have in 1 minute? Tell me.
60.
No. What's periodic time again?
Periodic time is time taken for 1 second, one oscillation to be completed.
So if I tell you the periodic time is 1 minute, how much oscillations happen in 1 minute? I feel like you're overthinking it. So periodic time is the time it takes for one oscillation. So listen, if if the periodic time is 1 minute, how much time it takes for one oscillation?
Oh, 1 minute.
Yeah, yeah. So if the periodic time is 1 minute, then if 1 minute pass, then how much oscillations would have been completed?
One.
One. Okay.
Oh
If my
yeah. Oh, I
periodic
think it.
time is 10 seconds now, so I decrease my periodic time. What that means is it's taking less time to complete an oscillation. So in 1 minute now, how much oscillations you gonna have?
Six.
Right. So by me decreasing the periodic time, what am I increasing?
The
The number
frequency.
of? Yes, the frequency. But let me take a little step back. Before frequency, we increase in the number of
Oscillations.
in the same time, which is frequency. Yeah. Because watch, and it's the same time?
Yeah.
Yeah, but we have more oscillations there because the periodic time is less. So if I double my frequency, then I would half my period. They're related opposite now. They cannot opposite each other, right? So the
Mm-hmm.
period of the output would be halved, right? So the generator is subsequently rotated, right? So the generator is subsequently rotated at twice the frequency. They want me to tell them what effect it will have on the value of the output voltage. What do you think will happen to the output voltage? Um, is a 1 mark question. See if you could guess. See if you can guess.
Oh, voltage.
What is it?
The output voltage mm, will increase.
No, nothing will happen. Nothing will happen. Yeah.
Huh?
Yeah, think about it, right? In the cars and stuff.
Yeah.
Okay. And you know how the alternators work on thing, right?
Yeah.
Okay, so when the tires rolling, that mechanical is have a conversion between mechanical energy and electrical energy, and that is charge the battery. And the battery is 12 volts.
Yeah,
You think when it go faster, the voltage is raised? Because remember, I did have to charge your 12-volt battery.
yeah.
You think your voltage will
Oh,
change?
oh no.
No, but you're going faster, right? So if you're going faster and you're going at a higher frequency,
Yeah,
but yeah, you're going at a higher frequency, but is the voltage changing? And it is still charging the battery at 12 volts?
yeah,
Yeah, it's still charging the battery at 12 volts because the frequency doesn't affect the output voltage. It doesn't. So no change. That's why they put one mark. No change. Right? We still have 20 minutes. Aliyah, good night. Good night. Blessings. Aliyah, you pick out your fast, fast. Pick out your. We're doing fast because.
Um, 2017.
Yeah, June 2017. Let me go. Okay, induced EMF. Oh, you didn't do this as yet. We are yet to do this. Motors are yet to do that. Nah. Uh, guys, until you remember doing thermodynamics. I remember that.
Yeah,
Like, the latent heat of vaporization, the specific heat capacity. I remember that. That's a little while ago, But we did do it. But we did do it, didn't we?
that was like a while, like real long kind of way.
Yeah, yeah, it was very long ago. But let me see if we can do this question, huh? Let me see if we do this question. Because this question have power and thing in it, so we gotta use some electrical. So, who wants to read it? Pass. I want to do one more past paper question after this. So somebody read it.
Um, the following data were obtained in an experiment using an immersion heater to determine the specific latent heat of vaporization of water. Read out the mass of, read out all that. Oh,
Nah, don't worry. Using the data above.
using the data above, calculate the specific latent heat of vaporization of water, assuming neg negligible.
This have all with it. Aliyah. Aliyah, wait.
No.
Aliyah, wait. This is why I can't do YouTube live, I'll get cancelled one time. Yeah. Negligible heat is lost to the surroundings, right? Negligible heat is lost, meaning that no, we pretending we didn't lose any heat.
Yeah.
No, let me see if I remember. In when we talk about latent heat, that is the energy required to. I'll give you a hint. When you're changing from like, let me just say water to ice, you need energy to do what? Talking about like the interatomic bonds, we need energy for
to join
chemistry.
them.
Well, if we're going from water to ice, you're not wrong. So the technical term is you need energy to reform bonds. So, and that has happened at 0 degrees Celsius.
Mm-hmm.
So, but in this case, we're talking about steam. So, if I'm going from water to steam, I will need energy to to change to change the structure. I will need energy to break bonds, right? So when we talk about latent heat of vaporization, is there a change in temperature?
Yeah.
Justin, Kirsten, Alia, is there a change
Yeah.
in temperature?
Yeah.
Justin, you agree?
Wait.
Yeah.
But yeah.
Latent heat of vaporization.
Latent. Yeah. Because anti-changing the state of matter.
Look back at your notes. Anytime there's a change in matter, the temperature does not change because all the energy is used to reform bonds or break bonds, not raise temperature. Let me explain what I mean, right? Let me explain what I mean. Aliyah, what's the temperature of your hand? Let me just say you have rectangular hands. I'll penalize the draw. But let me just say you have rectangular hands, right? He's a Lego person. What's the temperature of your skin? Tell me, Aliyah, what's the temperature of your skin?
Like 36.
All right. What if you hold a block of ice in your hand? Is it that the block of ice is melted water immediately at 36 degrees Celsius? Let me
No.
say that one more time. When you hold a block of ice in your hand,
Yeah.
does the ice melt? Does the ice turn to water and the water goes to 36 degrees Celsius immediately?
No.
When the ice melts, the water is 36 or it's still zero? I'm answering that question. When ice melts, as soon as it melts and it makes that transition, what do you think the temperature of that water is?
Um, it'll be 36 degrees, same temperature.
What? Okay, Justin, I want you to go in the kitchen right now and hold a block of ice in your hand. Will the block of ice turn 36 degrees Celsius?
No, it can still remain at 0.
You're right, Justin. When you hold a block of ice in your hand, right? When the ice melts, that water does be hot or cold? Think. I know
When
shame on you, but think. When if you hold a
when
block
what?
of ice in your hand, if you hold a block of ice in your hand, when the ice melt, like it now melting, the water does be cool or hot?
Cool.
Cool, right? So the water, so like when the ice melts, the water does immediately be 36 or is it real cold?
What is oh yeah.
It's be real cold.
Cool.
And then it go heat up to 36 after some period of time. So you know what I mean? That means that there was no change in temperature. When ice goes to water immediately after, we're talking about water at 0 degrees Celsius. What I'm saying is you need energy to reform and make bonds. That is not change in temperature. That's a change in molecular bonding. Aliyah, you understand what I'm saying?
Yeah.
Because think about it. Ice at 0 degrees Celsius, ice at 0 degrees Celsius, immediately after it melts, it will be water at what temperature?
0.
Right. Was there a change in temperature?
No.
What there was a change in?
State. State
Right.
of.
And we need energy to change states.
Yeah.
So the energy required to change state is latent heat of vaporization or latent heat of fusion. Right? So when you change state, are you changing temperature?
No.
Justin, are we changing temperature when you change state?
No.
No. Because the ice will melt to water at 0 degrees Celsius, and when it reach water, and then they get heated up. Like if you put a block of ice in a frying pan, would the would the ice immediately melt and turn into water at 100? Justin, like would it immediately do that, or the ice go out and melt first, and then when it melt, the water goes out to heat up? Which one?
Yeah. Um, when it melt to water, it will take time to heat up.
Exactly, right? So anytime I'll see the vaporization, latent heat. Anytime when I see latent heat, that we're talking about change in state, not change in temperature, guys. Right. Do you remember the formula for latent heat of vaporization? E is equal to,
MC delta theta.
no, that's for specific heat capacity.
Um, it could be E is equal to And
Yeah,
LV.
MLV. Right. E is equal to MLV, right? Awesome. So what do they want us to figure out? Using the data above, calculate the
specific latent heat of vaporization.
right. You see this LV here, guys? That is one thing, eh? That's not two terms. So E represents what? What does E represent?
Energy,
Yeah, energy. What does M represent?
mass,
Mass. And what does LV represent?
um,
Look out what the question asking. See if I can figure it out.
the
Yes.
latent,
LV is the specific latent heat of vaporization.
yeah.
Yeah. Right? So we would have to make LV the subject of the formula. Justin, if I make LV the subject of the formula, what would that be equal to?
To make LV the subject any formula.
Yeah, what would I have to divide by on both sides? What block in the
M.
LV? M. So
M.
you're gonna put E over M. Now there's one problem here. We could figure out the mass, right? Remember what I told you? Um, when we're talking about, well, we're talking about change in mass really. So if originally it was 0.28 kilograms and now it's 0.26, well, what was the change in mass? Can anybody figure out the the mass? The mass of the can anybody figure out that?
The change or like
Yeah. Let me explain
zero.
something, right? Let me explain something. We're talking about a change in state, right? A change in state. So you have a can of water and you're heating up that, right? You have an immersion heater. How do you know it's an immersion heater?
No.
An immersion heater is basically like an electric kettle I have in our kitchen.
Oh,
I just plug into the wall. That's what immersion heater is. Basically, what happened is, Justin Curson,
Yeah.
this over here is before you start boiling it, right? So that is when the water at room temperature. After you boil it, and some of the water would get hot and escape as steam. Does that make sense? When you boil water, enter this into steam. That makes sense.
Yeah.
And steam is just a gas is water, right? It's water. And then water have mass.
Yeah.
So until losing mass, if you boil water, until losing the water,
Yeah.
so you're losing mass. So could somebody tell me the mass of steam, the mass of water are lost because it turned to steam?
0.02.
Right, that would be the mass of water I lost because it turned to steam. Justin, tell me if that confusing you.
No, just minus it.
I just minus it, right? And that's how much water we lost. Water lost. And that's the water that turned to steam. Right. So we know what the mass is. We need to figure out energy. hmm Do you all remember the formula for energy? There's a formula for energy involving power and thing. Energy is equal to what? I thought I'd send you all the physics formula sheets a while back. Aliyah, Justin, Aliyah have the physics formula sheet.
I think it's on the group.
Yeah, it's on the group. Let me think about it, guys. So we have to find energy. Forget the mass. Well, what other pieces of information we have?
You have the time,
We had the time, and what else we have?
the power
So
of
make
the
a
heater.
wild, ridiculous guess. It's not crazy. What's the formula for energy is? Make a wild guess.
Um,
What's the formula for energy is?
it could be
PT equals to PT.
Yes, power by time. Oh, yeah, yeah, that's what I was saying that now. Because they gave you power, and they gave you time.
yeah, yeah,
So E is
yeah.
equal to power by time. Right. Now, the power is 150 watts. And when in physics, when we're working with time, we have to convert the time to what? Or what we
Seconds.
convert time to?
Seconds.
Seconds. So 5 minutes is actually how much seconds? I don't multiply that by what?
60.
Right. So what is 150 by 5 by 60? I say um 5. I think 45,000.
Yeah, 45,000.
Way about it. I real about it.
I
I
don't know if
know.
you probably calculate that already and just,
No, no, I did not calculate it. How I figure it out
okay.
is because I know 6 by 5 is 30, and I know 30 by 15 is 444, 45,
45.
4,500. Yeah, I know that. And I just add extra zero. Quick maths. Come on, come on. Right. So, and what is the unit for energy? Let me ask Justin. Justin Balchan.
Huh?
Kavir Justin Balchan.
Oh,
What is the unit for energy? Dare I ask?
no. Uh, Jules.
Joules. And so you remember me talking about
I get you.
um
Yeah.
the cannonball and experiment and thing?
Yes, yes, yes.
Count Rutherford and thing. I surely remember that.
Yeah, we remember
How
that.
he bored the hole and he realized that I was creating heat and it heat up the water because of the friction.
Yeah.
Yeah. All right. So latent heat of vaporization will be equal to the energy. My energy is 45,000 all over the mass. My mass is 0.02. Plug it into a calculator. Let me know. Yeah, guys, plug it into the calculator. I don't hear anybody. Hmm. Oh yeah, see you're unmuted, but I'm not hearing you.
2 million, 2,250,000.
2,250,000.
Yeah,
That's what you see, right?
yeah.
And let me try to figure out the units. Let me show you how we doing this, right? Justin, what's the formula for latent heat and vaporization?
Okay.
Right. What is the units for energy?
Jules.
Right? And what is the units for mass? Mass is measured in?
KG.
Yes. So the units could be what?
Jules per kg.
Exactly. Let's go. Let's go. 6 marks, guys. Ooh, 6 marks. Nice. The coil of the immersion heater was not completely submerged. Explain how this would have affected the value for the specific latent heat of vaporization. Okay, Aliyah and Justin and Kirsten. If the coil, if the, okay, all your electric heaters, right? And it have a coil in that. All you ever see what, you know what I'm talking about? Like it have like a metal coil inside, and that is go to the wall. It's plug it into the wall. You know what I'm talking about? For the electric kettle.
Yeah.
Yeah, if you don't fill it all the way, what happen?
If you fill it all the way,
No, no, if you don't fill it all the way, and the water not reaching the coil, will the water get hot?
mm,
It'll get hot, right? But you think it go heat up as fast as it should?
no.
No. So if the coil not directly, okay, if you put if you have the coil here, so we have the coil here, and is the coil reaching the water there? And Justin, and the coil is what, real hot?
Yeah.
And then that transferring the heat to the water.
Yep.
So if all the water is not fully submerged, right? If all the water is not fully submerged, will what will happen to the amount of water being um converted to steam? Will less water be converted to steam or more water converted to steam? Think about it. So will the water heat up faster or will the water take a longer time to heat up? Let me hear that. Alia, if you don't fully if the water don't fully cover the coil,
It wouldn't.
you think you think more water will get converted to steam or less water will get converted to steam? Make a guess. Think about it logically. For water to be converted to steam, right? And you need to heat it up,
Yeah, so less water.
less water. And if less water being converted to steam, our mass of steam, would it be less or more?
More. Wait.
More?
Less.
Less. Less because enter wouldn't be heating up all the water as good as I should. Because if the water not fully submerged, then watch. Then this all this part of the coil, it heating up the environment, heating up the
Yeah.
water.
Yeah.
So less water is gonna be converted to steam. So we're gonna have a lower mass. Right? We're gonna have a lower mass, right? A lower mass. So if I have a lower mass, from a mathematical standpoint, would that increase LV or would that decrease LV?
Decrease it.
Are you saying decrease?
Uh,
Let me look at it from a mathematical standpoint. If I say LV is 200 over 100, what will be equal to?
2.
Okay, and in this case over here, my mass was what?
100.
Okay, let me just drop 100 now. So we're decreasing the mass, right? Let me decrease it to say 10. What happened now?
It could
What
decrease.
happened? Right, because you're
No, it
dividing
could
it
increase.
less. It increased because you're
Yeah.
dividing
Yeah.
less.
Yeah. Yeah. Yeah.
So if the mass, if the mass of steam is decreasing, the latent heat of vaporization would?
Will increase.
Yes, yes,
Yeah.
yes, yes. That is how it works in here. So
Okay.
according to the formula, so the answer is LV would increase. The reason is less water would be converted to steam. So if less water getting converted to steam, the mass would decrease. And according to Justin, I feel like you're a little lost here.
Narrowly.
You sure?
Yeah.
Okay.
What if I get to do everything Talia?
What?
Ollie, you're Ramakan. Why you
What?
coming late to class? Anywho, according to LV, which is equal to E over M, if M decreases, LV increases. Right. So yeah, that's it. 3 marks. So you had to say how LV would increase. You had to say why. Less water converted to steam, the mass would decrease. And you had to say according to the formula, if M decreases, LV would increase because it's an inverse relationship. I feel like we could do one more past paper, and then we go one more past paper question, then we go start a new topic. So let me see. Um, anybody suggest a year? Suggest a year.
2012.
Wait, say that again.
2012.
2012. Okay. Wait, give me a second. Right. 2012. Let's see. Uh, 2012. Camera off. Yeah. Right. 2012. Let's see. Alia, you're bringing up the pass. Justin, you see? You see?
Exactly.
Ooh, it's a joke. It's a joke. I feel I might get in trouble, you know.
Uh,
Look at past papers. Hmm, Lord have mercy. Damn. 2012. Okay, 2011. 2012. Any minute now. Yeah, it's 2012. Let's see what questions you have. Hey, look, I tell you remember Snell's law and thing.
That was one of the craft we do, one of the lab.
Yeah, he's always in a lab with the Pyrex block hunting. Always. Yeah. Um, let us. Are we still in 2011? What? Ain't no way. Okay, I think I see a nice question here. A circuits question. But this is still 2011. Uh, I want to let's try this question. Come on, it's a circuits question, and we did a question extremely similar to this question last class. See if I could come up with a circuit diagram. Yeah. So, does anybody have any ideas on how to do question three? Aliyah, does this ring a bell to the last class?
Trying something.
Justin, Justin, you think you do something?
Trying something.
Nice. Aliyah, you see any connections with this and the question from 2024?
Um, I tried.
You remember 2024 question?
Yeah, that was with the open circuit.
Oop,
Yeah,
I
yeah.
gave the answer.
I have it, I have it.
Hmm. If I read the question, I'm gonna realize it's the same thing. So, Justin, according to the question, we want to make an experiment to do what? To check to do what? Tell me, explain.
To check and see which will be the best conductor of electricity, which one will be the best insulator out
Right,
of the six different materials.
right. They were given six identical samples of solids of different materials and asked to find out which was the best conductor. Right. If something is a good conductor, what do I mean? What could pass through it? Tell me, what could pass through it? Waiting. If something is a good conductor, what do I mean? Really, boy. Come nah. Justin Aliyah. Hmm.
A conductor is something that
Don't be reading anything from
allows
Google or ChatGPT, eh?
not
Don't be reading anything from
not
Google. Explain
Google
it.
is conductor is something or like a type of material that could allow the flow of electric current,
Yes.
like any type of
Yes.
metals. And a insulator is something that or like a type of material that blocks the flow of electric current.
Yes. Remind me, what is current? Current is the flow of what?
Electrons.
Yes. 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 So something is a good conductor if it allows electrons to pass through. Yeah, so after this question, we're going to start. I want to do VI graph. Yeah, I think I could start that. Right. So guys, I seen Justin try that thing, but Justin, that wouldn't get you full marks. You have to apply yourself better on that. Yeah, you look like you just copied the same thing from 2024. Um, Justin, so if we use a circuit, how are we gonna test these six identical samples? How are we gonna know which one is the best conductor? Think.
Um, tries like
How are we gonna
um
know? How are we gonna know is the best conductor? What in a circuit? Which element in a circuit could tell us is the best conductor?
the bulb.
Yes, the bulb. If it's the
If
best
it's
conductor, what happen with the bulb?
a brighter light,
Yes, they gonna light up the brightest. Perfect. And now you need to put that in B, description of the procedure. So apply yourself. I waited on an answer from Aliyah and Kristen. Aliyah, let me know what's going on.
Um, I draw a circuit, right?
Mm-hmm.
But like, I don't know.
Hmm. Submit.
I'm gonna fix it and then I'll send it.
All right. Okay, Alia, too much time pass. I go into put the answer on the board, right? Right. So Alia, you paying attention?
Yeah.
Okay. So you want to make a circuit where you could switch out components and see its effect on the circuit, right? You are given six identical samples of solids. If it's identical, wouldn't that also mean the shape and size, everything is the same? The only difference is the type of material,
Yeah.
right? So this is what we're gonna do. We're gonna make a circuit that has a bulb in it. The reason for a bulb is because, and you can see a bulb,
Mm-hmm.
right? And you can see if a bulb lights, and if it's not lighting, you can see how bright it is, whatever.
Yeah.
Yeah. It is the circuit I would build. And over here, you would just say place material or sample. Let me know if I don't understand that. And for the battery, you could use a simple 9-volt battery or something. So we have a bulb here, a bulb, switch, right? Alia, if something, how would we know if one of them is the best sample, best conductor? How would I know? Or what would I see in the bulb if it's the best conductor of electricity?
The light.
What about the light?
How bright it is.
Yes. So let me describe the procedure. Number one, set up the apparatus as shown above, right? Close the switch, place material or place a sample in the gap and record the brightness. The material or the sample that results in the bulb being the brightest is the best. Right. So let me know if you all understand that. Justin, you understand that?
Yeah, actually, I just keep my method.
Mm-hmm. Yeah, so just watch out for that. Alia, what about you? Let me show up my screen. Yeah, Alia, what about you?
I understand.
So yeah, you're just looking to see which material will give you um, the brightest, maybe bulb shiny brightest. That's it. Oh, look, they have observations right here. So you didn't have to put four over there. So I can put four on the observations because that's what it is. Oh, and look to split up the observations. So Alia, what observations are to be made? We need to look at.
How how bright or dim the bulb is?
Correct. So let me see that fancy. The light intensity of the bulb, or the light output of the bulb. Or we could say the luminosity of the bulb. Real fancy thing, you know. The light intensity of the bulb. You can say that, you can say the the luminosity of the bulb. Um, and the light output. And Justin, how would the observations be used to come to a conclusion?
Um,
How would I know which
so
one is
when
the best conductor?
in the end, the one that is the best conductor, um, the light will be the brightest. The light will be light of the brightest.
Right. The sample that the sample that is the best conductor will result in the in the sample that is the best conductor will result in the bulb. Okay, will result in the output of the bulb being the most. For right. So the sample that is the best conductor will result in the output of the bulb being brightest, or bulb or the output of the bulb being the most. Right. So that's it for that. When you all have that copy down, we'll move on to a new topic. Actually, I will send these notes out to our class. Don't worry. Let's move on to something new. I'm not gonna dilly dally. I'll send it. Don't worry. So last class we finished up circuits. We are done with circuits. There's nothing to be done in circuits again, right? Now we're gonna look at the resistive properties of wire. Right. So, Justin, a way to read.
Um, Current is the flow of electrons. Length longer wires have a greater resistance. The reason for this is because the flow of electrons will have a much greater distance to cover. Thickness, well, the diameter. Thicker wires will have a lower resistance because there is more space for electrons to move through.
Think of it like this. If you have a highway, okay, if you have a road, right, and the road have like 3 lanes, would it have as much traffic because our road was 1 lane?
No.
No. So that makes sense. The real reason why length results in greater resistance has to do with collisions and all kind of thing. But does advance, right? So you all copy that down. You all can copy that down. I wonder to change this because oh, because yeah, that more scientifically correct. I don't know where I get that definition from, right? An example of it is like this. Think of if it have re think of it like this. If it have real people in a party and it just have and if it have real people in a party and the room will be crowded and the room crowded, it'll be hard to move about. And think of it, what makes a good conductor is its ability to carry electrons. If the wire is really long and the electrons are colliding, it kind of hinders its ability to move. And if the electrons aren't moving as freely, then it would have more resistance. Because think of it like the electrons not getting to flow freely, it's being resisted. Makes sense. Ali, are you good?
Yeah.
Yes. All right, you all have this copy down. Resistive properties of wire. Um, Alia, you
Yeah.
have it copied down.
Yeah, finished.
Justin, what about you?
Yeah.
Right. So let me pick it up. If I have a wire and the wire is really, really long, okay, let me give this a couple of conditions. So condition one, we have a long wire that is just thin. As we would say, it's very maga, you know. Ooh. When last you hear that? When last time you hear that word? Oh yeah, you just hear that word? Can't hear anybody. Everybody went real quiet.
What word?
MAGA.
MAGA?
Yeah, you know, like how you can say
MAGA.
you're real,
Yeah, yeah, yeah,
you're
yeah,
like you're
yeah.
skinny now.
Yeah.
Anywho, which one which wire here will have the highest conductivity? Or in other
Um,
words, the least resistance?
the shortest one.
Yes. The reason why, some of the two reasons. If the wire is long, what will happen? The electrons will
It would have the electrons would like
think of it. If you have a long line, you're waiting, and it have a long line, and they
the
will take a long
electrons
time.
would collide.
Yes, yes, the electrons will collide. They can't go anywhere, and that's literally resistance. If the wire is if the wire is short though, they have a lower chance of that happening.
Yeah,
If the wire is thick, if the wire is thick, then you have a lower chance of the electrons colliding,
yeah.
right? You have more rooms for the electrons to move. So which
Mm.
wire here would have the most resistance?
Um,
Let me number it. One, two, or three.
hmm.
Which one would have the
One,
least resistance?
one.
I mean, sorry, most
Least
resistance.
resistance.
Most resistance. Sorry, most resistance.
Most resistance.
Yeah, most resistance.
One or three. I think one.
One for sure, because it's
Yeah,
very thin and long.
yeah,
Three is longish, but it's
yeah,
very
yeah.
thick.
Thick.
So
Yeah,
it the electrons could go. It wouldn't really it could have room to flow now. It wouldn't collide,
yeah.
right? Think of it like you have a bunch of anybody here know who is Naruto? Oh, they know who's Naruto? Who's Naruto?
Not really, you know.
Oh, yeah, that stuff. Um, anyways, imagine if like five all they were trying to run down the hall until they go collide and bounce off each other and thing. So
Yeah,
so most likely they wouldn't really reach the end as fast as possible. But if it had a wide hallway, then all they could rail run. Same concept here, right? Let me look at VI characteristics. Right, VI characteristics, and then we're going to look at finding resistance of an unknown resistor. This has come sometimes, right? That has come sometimes, right? Okay, cool. So VI, as you all know, the relationship V is equal to IR, and it says that voltage is directly proportional to the current. You know, good conductors like copper follow this rule and it's said to be ohmic. And we literally call that Ohm's law. V is equal to IR is Ohm's law. So if
yeah,
so good conductors, they follow that relationship and we say that they are ohmic, right? That means they are very good conductors. That means they conduct electricity no matter what. No matter what you do, you can flip the wire, you can turn the wire, you can twist the wire, it will conduct. So graph 1 and 2 are examples of conductors. They're just different kind of conductors. They're not perfect conductors like metal. Metal aren't perfect, but they're good. They're close to perfect, right? So you all are required to know these three graphs at this level. So copy down VI characteristics. Hey Justin, that drawing real bad. I like that. I like that.
Have a set around my room. I will different set of drawings.
Nice, nice. And yet your diagrams in physics classes be very interpretive.
Um, there's a
No, no. Hmm. No, it don't match up. It don't correlate.
not different story.
Yeah, so copy that down and let me know once you have it down.
That's Justin join on the group?
Yep.
I doubt.
Why you do that for? Because I hit diagrams
Because
in
yes, like
physics.
it don't add up. It
It do what
don't.
happens. That's why I see it.
The drawing's not drawing.
Mm-hmm. I feel you print that, you know.
I think so too.
Right. As soon as I have that copy down, let me know, please. And send pictures on the chat. I have to make sure I copy on the correct thing. Alia, you think the filament lamp does follow the rule V is equal to IR?
The who?
You think the filament lamp, the graph for the filament lamp, that's what it is a filament lamp. We need to label the graphs. So the first
Uh-huh.
graph is for metal, the second graph is for a filament lamp, and the last graph is for a semiconductor diode.
Right.
Do you think the filament lamp follows the rule V is equal to IR? First of all, V is equal to IR. That's a linear relationship, a quadratic wizard. If you compare it to Y is equal to mx plus c,
Aline.
a linear. So that's supposed to form a line, which is the only graph that obeys Ohm's law.
The first one?
Yeah, the first one. That's why we call it ohmic, because it follows Ohm law. Who would have thought? Yeah. So the first one. The others don't follow Ohm's law. They only follow Ohm's law for a certain part of it, part of the graph. Right, Justin, send your diagram on the chat. We need to see your graphs. Let me see your graphs. Yeah, Aliyah and Justin, are you gonna finish? Well, like killing time.
Yeah, I almost done. I just
All right,
haven't labeled the diagrams now.
no problem. After that, I wanna just go through fast with a semiconductor diode, and we're gonna look at finding resistance of an unknown resistor. That'll be for class today, right?
Okay.
Yeah, it just do add up. It do add up. Um, I want a little also write down the first graph is the only graph that obeys Ohm's law. Yeah, Aliyah, I didn't see your diagram on the chat.
I sent in it now.
Okay, right. So, this relates to the third graph, guys. The third graph, um, a semiconductor diode. Aliyah, I want you to notice something, right? Aliyah, Justin, and Kristen. What would the voltage be over here? Would the voltage be positive, negative? What would it be? Justin, Aliyah, Kristen, come on. What would the voltage be in this region?
There.
Zero. You can have it swapped. The x-axis is voltage. What would the voltage be over here? Aliyah, tell me. Let me just say this 0, 1, 2, 3, 4, -1. The voltage here gonna be what? Tell me fast, guys.
Negative.
The
Negative.
voltage could be negative. What would the current be? You see any
Positive.
current? You
Positive.
see any current increasing?
Yeah.
Wait, I'm talking about that region alone. That flat region. You see
Oh,
the current
no.
increasing?
No. No.
Where's the current there? Give me a value.
Negative.
Negative. Let me just leave it as 0. It's basically 0. If you read off the current, if you read off the value on the y-axis,
0.
it's basically 0.
Yeah.
What that means is when the voltage is negative, is any current flowing?
No.
No. When the voltage is positive, look how it's behaving. It's behaving good.
Yeah.
So, and when the voltage increase and the current increase and it's following Ohm's law?
Yeah.
Right. So we're gonna look at what a semiconductor diode is. Right, so Justin, when the voltage is negative, is any current flowing?
No.
No, because what's the current?
0.
0. What about when we have positive voltage? Do we have current?
Yeah.
Yeah, we have current. For instance, when my voltage is 2, where's my current? In this graph.
2.
Can I make up graph? Yeah. Right. So let me actually see what this negative voltage is about. Right, so this is what a semiconductor diode looks like. It's kind of, you could think of it kind of like an arrow, and it kind of indicates what direction current will flow in. So you all can copy that down, a semiconductor diode, and I will explain it. Or Aliyah could explain it to us. I feel Aliyah know about this. I feel Aliyah know what a semiconductor diode is.
I kinda don't, you know.
Make sense of it. What telling you a semiconductor diode is? You know what a conductor is?
Yeah.
Okay, you know what semi means?
Halfway. Yeah.
Halfway. So if I say something is a semiconductor, that means it's a halfway conductor.
Yeah.
All right, look at the graph. Justin, when the voltage was negative, was it behaving like a conductor? When the voltage was negative, was it behaving like a conductor?
No.
No, because what was the current?
0.
So was it allowing any current to flow?
No.
No, because the current is 0. But when the voltage is positive, I have current. So a semiconductor diode, as the name suggests, is a material that allows current to flow in only one direction. In the other direction is block current. It's like a insulator. Aliyah, you understand now? You can see from the diagrams that is only allowing current to flow in one direction.
What was that, sir?
It wasn't paying attention.
Bryce, come and distract me.
Yeah, yeah, someone will talk. Tell them, hey, I'm doing physics. Unless you want to learn physics, we could come.
Yes, he hear
Yeah.
him, yeah.
Well, let him join you then. You can do physics too.
He right here.
Once he not interrupting you.
No, don't worry.
And Aliyah, don't interrupt him too, eh? He doing physics.
No.
Don't interrupt him, right? Yeah. So Aliyah, what I was saying is semi means half. So half
Yeah.
conductor. That means it is allow current to flow in one direction, but it do allow current to flow in the other direction. So
Yeah.
one way it is act like a conductor, it act like metal, basically. The other direction is act like rubber or something. It do allow current to flow. So copy what I have on the screen. I'm gonna give Ollie a question.
Yes, it is.
Yeah, and Justin, I wanna see your diagram. I want to see what you're doing. But as you could see earlier, Justin is very talented, multifaceted. Hey, always see the video with Certified Samson
Yeah, the new
with
one.
Screws. No, with where the guy was interviewing Screws.
I don't think so. I don't think I'd see that one.
You see the one with Zion?
Yeah, yeah.
Yeah. You feel like I changed person now? Nah, Certified Samson, real bad though, you're real bad.
Yeah, he crazy.
He could be an artist if you want. Ice cream man, comedian, anything. In the video I'm talking about, he sing a Frank Sinatra song and thing. Right? So I'll wait and let's copy this down and I'll explain it and give all a question. Right. That's the plan. All right, so Leah, let me see your diagram. I'm gonna check out the diagram. All right, so I want somebody to explain to me what's going on in the first diagram. By the way, we following conventional current flow or electron flow? Which one are we following? Conventional or electron flow? Um, Anybody? Conventional or electron flow?
Conventional.
Yes. Remember we did that back a while back.
Yeah.
Um, Talks about conventional and the other one was electron at the start. Watch. Conventional and electron. We always use conventional, positive to negative. That's the standard now.
Yeah.
Right? Over here, I want to explain what going on there earlier. What going on? Tell me what going on in the first diagram, and Justin go explain to me what going on in the second diagram. Yeah, so earlier we have a circuit with a battery and a diode. The diode is connected in parallel in series. How? If you had to say that circuit looking like a series or a parallel circuit. Earlier, remember the criteria for a series circuit? Justin, you remember the criteria for a series circuit? Guys, Justin, you there?
Yeah.
I said series circuit. You hearing me?
Yeah,
Sorry.
yeah,
My
the
mic was
diode is.
on mute. My mic was muted.
Oh, I didn't hear you. But yeah, um, the diode is connected in series,
Yeah.
right? And I want to listen take down some extra stuff. This is like, oh, you don't need to know this one. Write it down anyways. Whenever a diode is hooked up in a way that it allows current to flow through, we say that it is in forward bias. And anytime a diode is in a position where it blocks current, we say it is in reverse bias. Just some additional knowledge. So earlier in the first diagram, is the diode in the direction of the current flow?
Yeah.
Right. Cool. So it allows current to pass through. Nice. It acts like a piece of metal. Justin, what is the difference between the first circuit and the second circuit?
The diode acting like a um insulator.
Right, but what did I change? Can you tell me what I changed in circuit two?
Only one um
See if you could tell the difference. Spot the difference.
the flow of current origin the other side of the battery. The like the bulb.
No, why the flow current change though? Why change? Why change in the circuit?
Um
If any, let's see it, tell me. Alia, if
the
you see it,
flow of
if you see it.
current.
Yeah, but why the flow current change?
Oh, because you're going from wait, negative to positive. No.
Right, that's not what I want to hear.
Hmm.
Aliyah, take a crack at it. What did I change in circuit 2?
What was that?
What did I change in circuit 2?
The direction of the current flow.
Both are the same thing. I understand
That
that, but why did the direction of the current flow change?
because the bulb not lighter. I don't know.
No. I want Aliyah. We basically playing spot the difference, you know. What is the difference between circuit 1 and circuit 2?
The battery is positive and the battery in circuit
Yes.
2 is negative.
I swap the battery. That's what I do. Watch. In this circuit, the positive is over here and the negative is over there. And in this circuit, it's swap. So if I swap the battery, the current go in the other direction. Justin, you not think of that?
I realized, but I didn't know what it was referring to that.
Oh, well, that's okay. Once you realize that is the only thing I change, right? If I want to make this circuit forward bias, what would I have to do with the diode? Tell me guys, if I want to make this circuit, if I want current to flow through this circuit, what do I do with the diode? Let me just say you're allowed to remove diode and change it.
You could turn the diode so face it
Like this. Wait,
no, you could like that.
yes, and that would allow current to flow through. Excellent. So that's why the graph looking like this is because when the battery terminal get flipped, it don't conduct any electricity. It current can flow. But when it's in forward bias, current flows as normal. Yeah. So you all good with that? Semiconductor diode. I take it as you all okay with that. So we finished with semiconductor diodes. The next class, I say I was going to do this, but it's a good bit to explain. And I want to do a past paper on this too. Next class, we're going to look at finding resistance of an unknown resistor. We're going to do past papers on that, and we're going to start AC current. Yeah, we're going to start AC current. AC versus DC, that kind of thing, right? So yeah, guys, let me see how much past papers we do today. One, two, three. And we'll do like 4 past paper questions. That's okay. So yeah, um, I see in some earlier. Well, nobody. Well, I see in Kirsten. Kirsten, I might see you tomorrow morning, right? And Aliyah, I will see you Friday again. Yeah, right. And Justin,
I
Justin, Justin. When I see you again, I see you Friday again too.
Yeah.
Yeah, right. Well, you will have a blessed night. Thank you for making it to class today. Later, everybody.